Shri Sai Ram. Welcome to the ninth part and the last session of this chapter, motion in a straight line. Having studied about the equations of motion in the last session, in this session we will study about slightly application of the motions of equations. So in this chapter we will be studying about the motion under gravity. Alright. So let us get started. So you can see there is a setup where the apple is falling down, vertically falling down. So when some object is falling down, what path it takes? It takes the straight line, right? Straight line, line joining between the 2 points, initial point and the final point. So it can be considered as the what? Rectilinear motion. So we can use our equations, kinematic equations which you have derived in the last session. But here we need to see what are conditions under the influence of gravity, and we need to substitute that values and get the result. Okay. So the motion under the gravity, that is the vertical motion. Here you can see a body is dropped vertically downward, that is the freely falling body we can call as, but here the V naught is 0, the initial velocity is 0. How? An object is released under the influence of gravity, it is said to be free fall where the initial velocity V naught is 0 and the acceleration is equal to g, and h, the s which we have denoted as displacement becomes the height here, because it is vertical motion. Here the vertical motion displacement becomes height, because this becomes height, and the acceleration which we are talking about is the acceleration due to gravity, because the earth is pulling the body, right? If the earth is pulling the body, the force which is being exerted on the body is due to gravitational force. The more about the force we will learn in the next chapter, laws of motion. As far as this body is concerned, it is experiencing a force due to gravity. How the force is acting on this body? In this direction, right? So the body's motion in this direction and the acceleration is also in this direction. We will derive in the chapter gravitation the value of g. Alright. So the acceleration due to gravity here, instead of a, we will denote as g. Alright. So as the body is falling down, so what is acting on it? It is being acted by a force called gravitation force, and it is being pulled down with the acceleration of g. So these are the conditions which we need to put in our kinematic equations. So what we need to put? Initial velocity is 0. To throw the ball down, should we impose any velocity? Should we throw with any velocity? Should we give any velocity to the body? No, right? Need not. That's why we call as a free fall. Free fall means we need not give any initial velocity. You just drop anything, it accelerates and it goes down. Should we throw down with any? Do we need to throw with any initial velocity to make it fall down? No, because the acceleration is already acting on the acceleration on it is pointing downwards, and the force is being acted in the downwards. So we need not give any initial velocity there. Alright. So initial velocity is 0 and the acceleration with which it will be moving is g. So now let us see how it is moving. It comes down. How it comes down? It comes down with the acceleration of g. So at every point the velocity is increasing, right? Because it is being accelerating from velocity v equal to 0, it will gain some velocity meanwhile, because this earth is pulling it. The earth is pulling it. If you know the g, if you remember your 9th standard physics, g is nothing but 9.8 meter per second square. So this is the value of g. With this acceleration, the body is pulled down. Alright. So the velocity after 1 second will be 9.8. After 2 seconds will be what? 19.6 meter per second. So it will increase in such a way. Now let us see the equations of motion. The kinematic equations of motion of a freely falling body is, we already derived v equal to v naught plus gt. here you can see A is replaced by G, H is replaced by H, S is replaced by H, and here also A is replaced by G. Here point to be noted, it is freely falling body. There the acceleration and the velocity are in same direction. Hence we wrote it is as a plus G. Alright. And also here X becomes H, G, A becomes G. So everything else remains the same. Alright. So using this only for the freely falling body, what we know? We know this becomes initial velocity becomes 0 for a freely falling body, right? So just substitute V naught equal to 0 in all the equations. What do we get? When the body is dropped freely, then V naught equal to 0, A equal to G, and S equal to H. That is the terms we already noted. V is equal to Gt. Final velocity is nothing but acceleration times time, product of acceleration due to gravity and time, because V naught is 0. As the time is increasing, what happens? The velocity will increase with the proportionality constant of G. That means the velocity is directly proportional to T. Just imagine if you have a object, this is the ground. So it took some time T1 to fall down. Okay. Now there is another object here. The ground is here now. Okay. So it took time T2 to fall down. Alright. So in which of the cases, if this is body A, if this is body B, in which of the cases do the object will attain more velocity? Of course, when it is traveling with more time, right? When it is traveling with more time, that means what? For that much amount of time, it is pulled with the acceleration due to gravity with proportionality constant G, right? More the time it is falling, more the velocity it is acquiring as it reaches ground. So V is directly proportional to T. As time is increasing, time of flight is increasing, time of descent we call as, time of descent is increasing. Descent means it is coming down from the highest point. As the time of travel is increasing, the velocity will also increase. This is basic intuitive thing. You can intuit. The second, H is equal to half Gt square. We already know from the equation H is equal to V naught T plus half Gt square. V naught T becomes 0 because V naught equal to 0. So only we are remaining with this term. So let us compare H and T, how they are changing. So H is equal to half Gt square, which implies H is directly proportional to T square. So with the proportionality constant G by 2. If you plot a graph between H and T square, half G will be your slope. Okay. So H is directly proportional to T square, and also T from here you can write as square root of 2H by G, right? If you only isolate T here and take everything on the other side, so it becomes square root of 2H by G. So H is changing, the H is directly proportional to T square. In the other words, if you want to see how the time is changing with respect to H, okay, if you have a maximum height H, so if you increase the H, how the time is increasing? If you increase the H, how the time is increasing? This is the relation. If you increase the time, how the H is changing? This is the relation. So this relation gives you this relation is between the height and time. How the time is related to H and how the H is related to time. Alright. The third thing, V square equal to 2gh. V square minus V naught square is equal to 2gh, actually V naught 0. So it boils down to V square equal to 2gh. So V is nothing but square root of 2gh. Now how the velocity is changing with height? Previously we saw how the velocity is changing with time. When the time of travel is more, the velocity it attains more. Alright. Here when the height is more, you also have the what? Velocity more, right? If I drop something with a greater height, it attains more velocity, but it is not linear, it is changing with the square root of h, right? H power 1 by 2. Now here it is what? It is directly proportional to t, but it is directly proportional to square root of h, alright. And the last point is, you can see here, anywhere did you see this acceleration due to gravity is depending on the mass? If I keep a 100 kg ball and a 10 grams ball, do you think the gravity which is acting on that ball is more than the 10 grams ball? Is there any mass here? There is no mass. That means the gravity is independent of the mass of the bodies, alright, when it is in the vacuum. The only force that is being acted on the body is acceleration due to gravity, alright. So there is no other force we are considering. So that is why we call it as a vacuum. There is no air drag, okay. If there is no air drag, air drag means there is no wind, nothing. So if the body is falling down, if there is a huge wind in this direction, that means there are two forces, one is which is acting downwards, one which is pushing sidewards, alright. So if you neglect this air drag, the only force which is acting on the falling body is the acceleration is the force due to gravity, alright. The force due to gravity is same for all bodies when it is traveling in the vacuum, alright. When the other forces come in picture, then what happens? The mass comes into picture. The heavy body will resist more, the smaller body will fly off. So there the equations change. But here, as far as this chapter is concerned, we are dealing with the vacuum. The acceleration due to gravity is same for all bodies, alright. So this is the case for the body which is freely falling. Now let us see the body which is vertically thrown up. Previously we have seen for the case where the body is falling down. Now let us throw up, okay. That is also vertical motion, that is also motion in a straight line. We can also use the kinematic equations of motion there, so use them there. So how they are moving? It is vertically moving up. The thing is, when you give some velocity to make the body project upwards, to make the body throw upwards, to throw the ball upwards, you need to give some velocity to the ball, right? Why you need to give the velocity towards the ball? Because the force of gravity is acting downwards. If you give some velocity to the ball, then only it will move up, alright. Otherwise it won't move. So we need to give some velocity to make it go up, but still the acceleration due to gravity, the force of gravity acting on the ball is downwards, okay. But see the animation, once again you will see, I am throwing the ball up. As it is going, but the acceleration due to the force due to gravity is downwards, right? That is mg, we call it as mg, okay. So it is acting downwards, that means g is downwards, velocity is upwards. Acceleration is downwards, velocity is upwards. In the 7th session, when we have discussed about this, about acceleration, we have already come across this, right? When the acceleration is one direction and the velocity is in the other direction, the speed decreases. Speed means nothing but the value of the magnitude of the velocity. That means you can imagine at one point it will slow down the velocity, that means the speed will decrease and slow down at one point and it becomes halt. At that point you will notice the velocity becomes 0, because acceleration is downwards, you are projecting the velocity in the upward direction, alright. So it will dominate up to certain extent, and then what happens? It will slow down and become stationary. This is what a stationary point, and then it falls down, right? So the final velocity here, if you consider this as initial velocity, here in this case the final velocity becomes 0, right? When you throw up, you are giving some velocity. When it is going to some position, some height, based on your what velocity you have given, it goes to some height and becomes the velocity 0, and this we call as a maximum height that attained by the body. Alright. So for this equation, what will be your g value? It is in the opposite acceleration is the acceleration due to gravity is in the opposite direction to the direction of motion. It is decelerating the object, right? The velocity is decreasing and going becomes 0 at last. That means we need to use minus g there. Okay, we need to use minus g there. Okay, so final velocity is 0, initial velocity is v naught, some velocity we give, and this h, this will be your h, and a will be what? Minus g. So that's what given, acceleration a equal to minus g, because g is in this direction, velocity is in this direction. So if you take this as positive, this as negative, opposite to the direction of motion. All right. A equal to v naught minus gt, it becomes, okay, final velocity is equal to initial velocity minus gt, because g is negative here, that is the reason it become minus gt. Now we already know final velocity is 0 here, that means initial velocity is equal to gt. All right. So from here you can write in v naught is equal to gt. All right. Here you can write this, some initial velocity it gave, how much height it took from here to here, some height it traveled, some position it changed. So v naught t minus half gt square. V square minus v naught square is equal to minus 2gh. Where there is g, we need to put minus. All right. So let us see how they are changing. Angle between the velocity vector and acceleration vector is 180 degrees. You know that, right? The velocity is going in this direction because I am giving the velocities in this direction, and the acceleration is in this direction. So they are anti-parallel. When they are anti-parallel, this is velocity vector, this is acceleration due to gravity vector. So these two are in 180 degrees. Cos 180 is what? Cos 180 is minus 1. All right. Now these are the equations for the body vertically thrown up. Now let us see how these quantities are related to each other. All right. At maximum height, v equal to 0, a equal to z. When the body reaches at maximum height, there at that point, after that point what happens? It comes down, that means that is a stationary point. At that point, acceleration equal to z, final velocity equal to 0. So what will be the time there? What will be the time? What will be the height there? Height is equal to nothing but v naught square by 2g. Final velocity square minus initial velocity square is equal to 2gh, right? Final velocity square minus initial velocity square is equal to 2gh. Now this is 0, g is going upwards, that means that is 0 in this motion. So this minus cancels. So h, that is maximum height, is equal to what? V naught square by 2g. All right. So this is the relation. So h max, so how much height you are able to get depends on your initial velocity. If you give your initial velocity more, your height will be more. If you are given two bodies of different velocities, one body is having a v01 velocity, one is having v02 velocity. Okay, depending on that velocities, the ratios of their velocities velocity square will be equal to the ratio of their maximum heights. Yes or no? See, h1 by h2 is equal to, because this is proportional. Okay, if this is the height attained by the first body which is having the initial velocity of v01, some velocity. This is the height of the second body attained by the second body when it is traveling with the initial, when it is traveling with the initial velocity of v02. The ratio of their heights is nothing but the ratio of the initial velocities whole square. So that is what given, because they two are related in this fashion. Alright. So these are the small things you can play with the equations and you can analyze conceptually. So TA equal to TD equal to V0 by G. What is TA and what is TD? TA is nothing but time of ascent. That means time of ascent means time it took from the ground to reach the maximum point. Okay, if this is some ground, okay, ball is projected in this direction and reached some height. This is h. Okay, the time it took to go up we call as time of ascent. The time it took to come down we call as time of descent. Alright. So time of ascent is equal to how much time it takes to go from ground to the maximum highest point is the same time it takes to travel from maximum highest point to the ground. Alright, because there is only force which is acting on the particle is the force due to gravity. There is no other force, right? So the time it took up should be equal to time it took down. So how do we prove this? So use the first equation, V is equal to V0 plus GT. Alright. So when the body is falling down, what happens at this point? When the body is falling down, free fall, what is the initial velocity? Their initial velocity is 0. Final velocity will be equal to what? GT. T will be equal to what? V by G. Okay. Now this is the when the body is falling down. When the body is projected up, if it is projected with the some velocity V0, initial velocity V0. Here you can see when the body is falling down, it is attaining some velocity. It is attaining some velocity, right? When it attains some velocity, if it attains some velocity V, if it attains some velocity V as it is coming down, with the same velocity if I project up, it will attain the same height, yes or no? If I project the body with the same velocity upwards, it will go to the same height, right? So use the equation for the body vertically thrown up. So initial velocity there will be V, initial velocity there will be V, otherwise you can call as initial velocity of V0, then you need to make here as V0, because to make the magnitudes equal I am considering V0 in the both cases. It is attain the value of V0 here as it drop down. So as I throw, I am throwing with the same velocity, so it can reach the same heights. So I can compare these two cases. Okay. So for that matter, what I need to do is I need to change this. I need to change this to some, for example, let it be U. This is the initial velocity. So initial velocity for the freely falling body is 0 here. So when it goes there, what happens? I have given some initial velocity. So it goes there and the final velocity will be what? If I give some initial, so initial velocity is what? 0. I am sorry. So the final velocity when it goes up is what? It becomes 0. I am throwing with what velocity? I am throwing with what velocity? I am throwing with the velocity of v naught. Okay. So, how the acceleration is acting? Acceleration is acting in the opposite side. So, it will be minus gt. So, v naught is equal to gt, t equal to v naught by g. This is time of ascent, this is time of, sorry, this is time of descent, this is time of ascent. All right. So, with the time of descent is this, I throw it with some velocity, it attained some velocity v naught. With the same velocity again I threw up. Okay. So, it becomes time of descent, it becomes time of ascent. See, those two are equal. Time of ascent is equal to time of descent. So, you can write, so I hope everybody noted it down if you want to note. So, from here you can write t is equal to ta plus td. This t is nothing but we call as time of flight. Time of flight. That means how much time the body is in air, how much time the body has travelled. It is time of ascent and time of descent, going up and coming down, whole together we call as a time of flight. So, time of flight is nothing but Ta plus Td, that is 2 V naught by G. So, time of flight is, what we can say, time of flight is directly proportional to V naught. How much velocity, if you give more velocity, time of flight will be more. If you give less velocity, time of flight will be less. So, that is having their proportionality. Alright. So, in the absence of air resistance, time of ascent is equal to time of descent. In the same way, in the last case we have discussed where the acceleration due to gravity is equal to for all the masses when it is in the vacuum. In the same way, this we need to consider time of ascent and time of descent are equal when we neglect the air resistance. If you have an air resistance, then time of ascent and time of descent may be changing. But as far as this chapter is concerned, we don't consider that air resistance. It will be so much negligible, so that time of ascent and time of descent will be equal. All right. So, these are the motions, these are the conditions we are employed for the two cases where the body is freely falling and the body is projected vertically up, and we used kinematic equations in it and solved for each case. All right. I hope you got the clarity on the kinematic equations and their application in the motion under gravity. So, now let us solve one example using the kinematic equations of motion. All right. So, let us see this example. In this example, he has given two objects. One object is moving at 70 kilometers per hour, second object is moving at 60 kilometers per hour. Okay. Now, if body B starts decelerating at 20 kilometers per hour when the distance between them is 2.5 kilometers. So, as you can see, V is having more velocity, A is having less velocity. At some point they may meet. Before meeting, when the distance between these two objects becomes 2.5 kilometer, this body B starts decelerating at what rate? At 20 kilometer per hour. All right. So, now he is asking what is the total distance travelled by body B, which is very easy. And the second thing, interesting thing is, at what time do A and B meet each other? These are the two questions. So, let us draw the diagram first again. See what is given. This is B, this is A. It is moving with velocity 70 kilometers per hour. B. It is moving, A is moving at 60 kilometers per hour. Alright. Now let us suppose they two are meeting at the time t, after the time interval t. Okay. So after the time, for example, some at this point they are meeting, object A, object B, A, B, they are meeting at this point. So after time interval t, if it takes time interval t, how much distance each of the object could have travelled by that time t? We are considering if they meet after t seconds, so what will be the distance travelled by A? What will the distance travelled by A in t seconds? Let us see. Let us XA. XA, distance travelled by X in t seconds. XA is nothing but, it is not accelerating, so it is simply, it is moving with, it was moving with velocity 60 kilometers per hour, 60 kilometers per hour into this time, how much time it took to be there. So this is what, 60t to go there. Now how much time did B took to go there? Alright, let us see. So it was travelling with 70 kilometers per hour. It was travelling with 70 kilometers per hour, but when these two, when the distance between two bodies become 2.5 kilometer, it starts decelerating. Alright. So the initial velocity of this body will be 70 kilometers per hour. So then we will calculate the distance travelled by the body, and we know the how much deceleration it got. So let us see. So xb, distance travelled is what, 70t, initial velocity is 70t plus half, g will be minus or plus, the motion in the positive direction, it is decelerating. That means what, it is making the velocity slow, it is making the body slower, that means acceleration is acting in the opposite direction, it becomes minus g, it becomes minus g, I am sorry, it is not g, it is a, it is not motion under gravity, right, minus a into t square. Alright, so it becomes what, 70t minus half, how much it gave you, he told you the acceleration, you can see the acceleration is, deceleration is 20 km per hour. So it becomes into 20 t square. Alright, so that becomes what, 70t minus, this cancels, 10 minus 10 t square. This is distance travelled by B for the time t. Alright. So what is the relationship between these two? We have added acceleration here. That means there is some relation between these two, because when the deceleration actually started, it started when the two are 2.5 kilometer distant apart, right. That means xb minus xa, when it is 2.5, then we have this acceleration. Okay. So we know that the difference between the distance is equal to 2.5, right. So xb minus xa, xb minus xa is equal to what, 70t minus 10t square, 10t square, 10t square minus 60t. Now what is the difference between they two? What is the displacement between they two? It is given 2.5, right? Now what is this xb minus xa? A is the observer, right? Relative distance of B with respect to A. Now for B, 2.5 is in the backward direction, right? The B is approaching, A is there. So when B is approaching towards A, if this is A, this is B. As the B is approaching A, when it is at 2.5, when it is at 2.5 kilometers, then it started decelerating. Okay. So the relative displacement for A with respect to, for B with respect to A is what? The observer is A. So B is approaching towards him. At that point 2.5 will be in what direction? The motion is in this direction. Relative displacement is in opposite direction. Alright, that will be minus 2.5. Okay, 90 minus 60t is what? 10t minus 10t square. Alright. So what happens now? It is all in terms of t, just solve for t. 10t square minus 10t plus 2.5 plus 2.5 is equal to 0. This is t. So 2.5 ones are 2.5 fours are. It becomes 4t square minus 4t plus 1 is equal to 0. This is in the form of t minus 1 by 2 whole square is equal to 0, which implies t is equal to 1 by 2. Okay. Here t is hours after t hours, because it is given in 70 kilometer per hour. So t is measured in hour here. So if they meet after t hours, then what it will be? We solved as t equal to 1 by 2. That means it is coming at half an hour. Half an hour means 30 minutes. So after half an hour, they two are meeting. So by the time half an hour, how much this B travelled? It is very easy now. So you can just write what is after t equal to half an hour, both A and B meet each other. All right. So in this time, how much B travelled? Same, xb, plug that xb is equal to 70 into half, 70 into t, 70t minus 1 by, what is the deceleration? 20 into t square, 1 by 2 whole square. That becomes 35. So 35. So 35 minus 10, 10 by 2, 10 by 4. So 4 ones are 4, 2.5s are. That becomes 32.5 kilometers. So xb travelled 32.5 kilometers. All right. So after travelling 32.5 kilometers, they two met. So after how much time they met? They met after half an hour, 1/2 hour, that means half an hour, 30 minutes they met. So this covers the kinematic equation, this application, and also the relative velocity. So what basically we have done the relative velocity. If you have seen here, what this equation tells you here, what this equation tells you, this is the relative velocity of the two. This is the relative velocity of the two people, right? This is the relative velocity of B with respect to A, right? What is the relative velocity of B with respect to A? V AB is equal to VA V VAB is equal to VA minus VB. Alright, what is VA? 60. What is VB? 70. Okay, so 60 minus 70 will give you VA minus VB. Sixty minus 70. So 60 minus 70 will give you 10. 10 into t. So the initial velocity, initial relative velocity is 10t, because they are starting at, one is at 70 km per hour, the next one, this is starting at 60 km per hour. The relative velocity of A with respect to B is what? Minus 10t. So you can write in that equation, then when you write minus t, then what happens? It minus 10t, then what happens? It becomes plus 10t square. Why it becomes plus 10t square? Then the relative acceleration will be positive. Okay, then the relative acceleration will be positive. Then it will 10t square, then the relative displacement will be positive. So the signs will change. So you can also derive in terms of relative velocity. You can also derive in terms of individual distance, how much it traveled in time t, and then subtract each other and then equate to 2.5. When you equate them to 2.5, you will get the value of t, that equal to half. After that, the plug in the value of t here, then you will get the distance traveled by object B. All right. So this is how we need to calculate. So this is in the relative velocity, you need to see this is VAB, this is XBA. So when you interchange the signs, every sign will change. So you will get the same result, but the signs will change. That's it. If you take the velocity of B with respect to A, it becomes 10t. So that will be 10t, that will be equal. So anyway you can change, you can just play with these equations. Alright. So I hope in this chapter everything is clear, right? First we started with displacement, what the motion is, how the rest and motion are related to each other, and then we have calculated about the speed, and then we have calculated, we have studied about the velocity, then slowly we went to calculus, then we introduced the concept called differentiation and integration. When there is a slightest change in time, slightest change in displacement, how the values approach, how the values of the ratios approach. Then we started about instantaneous velocity and average velocity, and then acceleration and the graphs related to that, how the graphs, position time graphs will give you, what is the slope of position time graph will give you velocity, what does the slope of velocity time graph will give you acceleration, what does the area under the velocity time graph will give you displacement. And then having covered all the basic concepts, we have derived kinematic equations of motion. Then one more application, we have derived motion under gravity. So this is all the chapter we have got for the motion in a straight line. I hope you have enjoyed this chapter. in the next chapter we will be studying about the laws of motion. For example, if you just think, when an object is moving and there is no acceleration, then what happens? Initial velocity is equal to final velocity. That means you need some acceleration to make the velocity change. When you have the acceleration, that means you are under force. That is the first law of motion. Informally, if you have a force, then only you can change the velocity. Alright. So this is informal introduction. We will explore more in the next chapter, laws of motion. I hope you understand this session and also this chapter, motion in a straight line. Go back and refer your textbook, solve some problems, approach your instructor and be curious. Till then, thank you. Sai Ram.